Greetings! Join me in the laboratory to see how we melt aluminum and make a tornado in it, in attempt to make Metal Matrix Composites. Metal Matrix Composites, or MMCs in short, are made of matrix metal which is strengthened by reinforcement material, resulting in a some way superior material. Reinforcements come in many different shapes. It can be particles, short fibers and whiskers, continuous fibers, or laminated sheets. The problem appears when some metal pairs don't want to stay together in orderly fashion as shown in my schematics. And the prices of MMCs in the market reflect the increased difficulty of making these novel materials. For example, regular aluminum costs around 5 euros per kilogram, but if you add only 1% of weight of nanoparticles in it, the value of finished product can rise by a magnitude. The same goes for ODS steel, which is already in use in the nuclear industry. Scientists have devised many intricate approaches for manufacturing MMCs. Main manufacturing challenges are to produce MMCs through metallurgical processes, where alloy is liquid. Today, I'm going to show you experimentally some successful approaches and also ineffective attempts. Let's move to Institute of Physics, where we can do experiments with molten aluminum. We start by taking aluminum alloy and melting it using an induction heater. Rapidly changing magnetic fields melt aluminum contactlessly, and when it's fully melted, we add nanoparticles. These silicon carbide reinforcement particles are made out of metal oxides and are tiny, measuring only 50 nanometers. To make a high-performance aluminum alloy, you want these particles to be homogeneously dispersed. Only then they improve mechanical properties of the alloy. Simply pouring them on surface leaves you with clusters of particles on surface due to poor particle wettability and van der Waals forces, which hold particles in agglomerates. To solve this challenge in industry, mechanical ultrasound treatment is used. Here, 18 kHz waves jiggle the metal, which helps removing dissolved gases in molten metal and also aids in nanoparticle dispersion in it. Visually, nothing interesting happens, but the process creates a unique and unpleasant screeching sound. Take a listen. We want a similar metallurgical method, but without a direct contact with metal. An electromagnetic method. Mechanical stirring, like you would simply do it with food, work for some particle and metal pairs. Unfortunately, due to density difference and surface tension, not for all pairs. So we have to get more creative. Our approach is to make more intensive electromagnetically generated flow in molten aluminum, and then try particle in-mixing. We do that by using rotating permanent magnet technology, which can induce intensive flows in liquid metals. Characteristic flow velocity is around 1 meter per second, which creates large surface deformations, forming a large vortex in which we pour in the particles. Another trick is to vary aluminum temperature. To change surface properties, we can heat aluminum a couple of hundred degrees above its melting temperature. Or more interestingly, we try to keep it at exactly the melting temperature of the alloy. This creates interesting conditions when metal has consistency of an ice slurry, similar problem you meet when making pancakes. If you pour flour directly into milk, it clumps together. You can divide the clumps by mixing it, but it takes time. It is way easier to in-mix flour in a more viscous media, such as eggs, or preferably egg-flour combination. The same idea is used with semi-solid aluminum mixture, which can be still stirred, and in the increased viscosity effect is exploited before casting the metal. This process is also called stir casting. When composite sample is created, we pour the processed aluminum in a graphite crucible, thus making small sample ingots to be examined later. Here is a unique point of view footage of that happening. You can see the phase change and follow the solid-liquid interface as metal solidifies. Another visible change is in density. Solid aluminum is denser, thus it takes up less volume, and this is root cause to many casting defects. Main point of this research is to make stronger alloys. Therefore, one of the main measurements of the sample is its tensile strength. These samples are made in a preheated casting mold, where on one side metal is poured in which then fills the second column from bottom to top. In that second column, samples of specific size are taken out, and then machined, heat treated, and then sent to tensile stress testing. Only then we know whether we have succeeded in making a better alloy.
Thanks for watching, and if you have any questions, please feel free to ask them in the comment section below. If you enjoyed this video, I suggest you check out our other ones, for example, how we levitated molten aluminum, or how we work with dangerous liquid sodium.